Welcome to this introductory video on advanced queuing models. In the previous set of slides on queuing theory, we talked about the fundamental concepts and basic assumptions of queuing theory, and we also introduced the formulas needed to calculate the steady-state performance measures for simple queuing models, and then we used these formulas to solve several queuing network problems. In this video, I'm going to give a very brief introduction to more advanced queuing models. We will then discuss some of the extensions to the basic queuing models and present the queuing formulas developed to analyze them. However, this time we are only interested in drawing inferences using these formulas to enhance our understanding of these models rather than performing the actual calculations. Here you can see a list of common extensions to the basic queuing models that we discussed in the previous set of slides. The first extension that we're going to discuss today includes single or multi-server queuing models with general arrival and service distributions. Remember, one of the basic assumptions in the previous models that we discussed was that the arrival and service processes were all Markovian. In a GGC model, however, we consider a more general situation where inter-arrival times and service times follow a general distribution with a known mean and standard deviation. Next, we are going to talk about how we can model the case where we have a network of GGC stations connected to one another. And then in the third extension, we will discuss machine failure and the queuing formulas developed to analyze the case where the server is not reliable. We will then very briefly introduce some other extensions, including multi-product queuing models, batch models, and finally closed queuing networks, and models where we limit the amount of work in progress or WIP. Now, remember when we talked about the basic queuing models in the previous set of slides, we mentioned that those models give us the exact analytical results. However, as we relax some of the assumptions and move towards more realistic models, like the ones that we're going to discuss here shortly, it is not possible to derive exact mathematical expressions for different performance measures at steady state. As a result, most of the models that we discuss in this video are approximation models. Moreover, as the level of complexity increases, the accuracy of these approximation models decreases, which makes simulation a better tool to study complex systems. But although the models we're going to discuss are not exact, they can still be very useful since they provide valuable insights about how these systems work. And as I mentioned earlier, this time we're not going to do any calculations using the formulas presented here. Instead, we are going to develop expectations about the performance of queuing systems based on what we learn from these models, as you will see later in the video. So let's start with the first extended queuing model, which is a GGC system. As you can see, we have a station that has a single server or multiple parallel servers with an infinite buffer. The only difference from the previous models is that here, instead of a Markovian arrival and service, these stochastic processes follow a general distribution. In other words, we assume that entity inter-arrival time follows a general distribution with a given mean and standard deviation. Similarly, processing times are also distributed according to a general distribution with a known mean processing time and a standard deviation. Now, given these assumptions, the timing queue and timing system for this station are given as follows. The timing queue for a GGC station, here denoted by CTQ-GGC, as you can see here, is approximately equal to this expression that we're going to talk about shortly, times the timing queue for an equivalent MMC system. An MMC system with the same number of parallel servers in this station. For example, for a case where we have a station that looks like this, meaning that we have two parallel servers in our station, and we have general arrivals and general service times, our timing queue is approximately going to be equal to this expression times whatever timing queue we have for a similar system but with Markovian arrivals and Markovian service. And of course we know how to calculate this second expression right here using what we learned from previous slides on queuing models. Now remember, the coefficient of variation is a measure of variability, which is defined by standard deviation divided by the mean. And a higher coefficient of variation suggests a higher variability, and a lower coefficient of variation suggests a lower variation in the stochastic process. Now let's think about what this expression actually means and what it tells us about a GGC system. According to this formula right here, the timing queue is directly related to the variability in the arrivals and service. Based on this formula, waiting time in the queue is expected to increase if the variability in the arrival process or the service process or both of these processes increases. As a result, this formula shows us that in a GGC system, in general, we would like to reduce variability, either the variability of the arrival process or the variability of the service process. And finally, the second expression simply shows us that the time in the station, in the whole station, is going to be the timing queue plus the expected service time. The last comment I would like to make about the GGC approximation formulas that we presented here is that our formula is also valid for an MMC system, where the inter-arrival and service times are exponentially distributed. Now, from your probability background, you should know that the coefficient of variation of the exponential distribution is 1. In other words, the mean and variance, or the mean and the standard deviation of the exponential distribution are the same. Therefore, this expression we have is going to be equal to 1 for an MMC system, and therefore we will end up with the timing queue equal to simply the timing queue for an MMC system if we replace these two parameters with basically 1, which is the coefficient of variation of a Markovian process. Now that we know the approximation formula for a GGC system, let's see how we can go one more step forward and analyze a network of GGC stations. So let's consider the case where we have two stations in series. In other words, we have the first GGC station where parts arrive from an external source, And then after parts are processed in the first station, they're transported to the second GGC station. And basically what we're interested here is to calculate the steady state results for this second station right here. Remember in the previous slide, the mean and variance of the external inter-arrival time to the GGC station were known, which we used to calculate the coefficient of variation of the inter-arrival times into our station. However, here for the second station, the coefficient of variation of arrivals is not given, but we know that it is going to be equal to the coefficient of variation of inter-departure times from the first station. In other words, in order to be able to approximate the steady-state performance of the second station, we need to know the inter-departure times from the first station. Fortunately, there is a formula to approximate the squared coefficient of variation of inter-departure times from a GGC station, which is given here. The coefficient of inter-departure times from the first station is going to be equal or approximately equal to this long expression you see right here, where U is the utilization of the first station. Here we have the squared coefficient of variation of the external arrivals into the first station, and this is the squared coefficient of variation of the service times of the first station, and finally we have the number of parallel servers in the first station. Now that we have the characteristics of the inter-departure times from the first station, we can use that information to calculate the timing queue and other performance measures for the second station. So based on what we have, the timing queue for the second station here is going to be equal to the squared coefficient of variation of inter-departure times from the first station plus the squared coefficient of variation of service times of the second station divided by 2 times what we previously had, which is the timing queue for an equivalent MMC station. Note that this formula is the exact same formula we had before, with only one change, and that is instead of the coefficient of variation of the external arrivals, here we're using the coefficient of variation of the inter-departure times from the previous station. Also note that the first formula suggests that the variation in the inter-departure times from the first station not only depends on the variation in the arrival and service processes, but also on the number of parallel servers and the utilization of the first station. Finally, remember that in an MMC system, the departure process is also going to be Markovian, and thus we do not need to be worried about the inter-departure times from the preceding station. In fact, in our approximation formula, if we replace the coefficients of variation for the arrival and service to 1, we will end up with the coefficient of variation of departures equal to that of the arrivals, which is exactly what we expect to have for an MMC system. The last common extension to basic queuing models that we are going to discuss in this video is machine failure. We all know that in a manufacturing setting, one of the most common types of disruptions in the production processes is machine breakdown. However, this model can also be used for any other types of disruptions in the processing of jobs. Basically, any disruption that occurs periodically can be modeled or captured using this concept of machine failure. For example, consider a restaurant or a store where the cashier needs to change the cash register tape periodically. And when you think about this process, you will see that we can also model this uh, uh, process of changing the cash register tape as a machine failure, because essentially the net effect of that is that the cashier won't be able to process jobs or won't be able to check out customers when the machine is out of tape. Now let's see how we can model machine failures using queuing theory. The first thing we need to define is something called machine availability. In simple words, availability is essentially the long-run average fraction of time that the machine is up and working. Therefore, availability is computed as the expected time to failure, which is the machine uptime, divided by the uptime plus the downtime, which is the expected time to repair. Based on what we have here, we can then define the notion of an effective processing time, which is given by the normal or the uninterrupted processing time divided by the availability. Now, note that essentially what we're doing here is that we are capturing the effect of machine failures by assuming an effective processing time that is larger than the normal uninterrupted processing time. And we know the expected value of the effective processing time is larger than the expected value of the normal processing time because our availability for a machine that is subject to failure is going to be strictly less than 1. Given the above, and assuming exponentially distributed time to failures and general repair times, the squared coefficient of variation of the effective processing time can be calculated using this formula. Now we have all of the information we need to analyze the steady state results for a GGC system with machine failures. All we need is to use the expected value of the effective processing time instead of the expected value of the normal processing time, and the coefficient of variation of the effective processing time instead of the coefficient of variation of the normal processing time in the formulas that we discussed in the previous slides. Now, again, as we mentioned before, in this video we're not interested in doing any calculations, but rather deriving insights from these formulas. Now let's take a closer look at these formulas that we just presented here. What we expect to happen when we have machine failure is that parts spend on average a longer time in the processing station, and also we expect the variation of the time that parts spend in the system to increase. Now let's see if our formulas also reflect these two expectations that we just developed. Since our availability is strictly less than 1, we already discussed that our effective processing time is going to be greater than our normal processing time. So our formula is in line with our first expectation. Secondly, if you look closely, we have the squared coefficient of variation of the effective processing time equal to the squared coefficient of variation of the normal service time plus a positive value, which shows that in the presence of machine failures, the variability of the time that parts or jobs spent in the processing station is also increased. So far, we talked about some of the common extensions to basic queuing models. However, there are many other exact and approximation models that have been proposed. In this slide, we introduce some other advanced queuing models. However, unlike the previous ones, we will not discuss the mathematical expressions in detail. This is just to give you a feel for what other queuing models have been proposed. So the first extension that we're going to introduce here is the multi-product queuing model, where everything is maintained by product type, meaning that different products have different probabilistic flows and different processing time characteristics associated with them. So queuing formulas are developed to analyze such systems where you have multiple types of parts or jobs that are processed in the queuing network. Also, different types of batching have been modeled using queuing theory. Batching is a strategy for reducing setup times and transportation costs, essentially. And here we see three different forms of batching that have been studied before. The first model is called batch forming process, where you can see the batches are formed after single unit processing and are transported to the next workstation. In the second model, we have what we call an oven batch service, where jobs arrive and get processed in batches. So we have batch arrivals and batch processing, while individual jobs are transported to the next station. Finally, in the third form of batching, we have basically jobs arriving in batches. However, items in a batch are processed separately, and jobs leave as individuals as soon as their processing has been completed. Finally, we have WIP limiting control models. The idea of these models is to control the inventory within production and manufacturing facilities to reduce costs. In the constant WIP or the con-WIP model, which you see on the left, the system is loaded with a desired number of work in progress, and then a new job is released into the system only when a job leaves the system. In this way, we can maintain the constant work in progress in the system. The second WIP limiting model, which you can see here on the right, is a form of the Kanban control policy, where we limit the number of work in progress that can wait at each station in a serial line. Therefore, a job is not moved to the next station until a space becomes available in the buffer of the next station. Since we limit the number of jobs at each station in the queuing analysis, we generally develop approximations for the number of jobs in each workstation somewhat independently, and then aggregate these results to estimate the performance measures for the entire system. Here is a short in-class assignment to put to test what you've learned from this video. Consider the above queuing network consisting of 4 single server stations where all arrivals are Poisson and processing times are exponentially distributed as well. For each of the following 2 scenarios, what you're expected to do is to answer these questions using your intuition rather than doing any actual calculation here. you should be able to develop an expectation of what will happen in each case based on what you learned in this video. In the first part, suppose that machine C is not completely reliable. The time between machine breakdowns is exponentially distributed with a mean of 4 hours, while repair times follow a log normal distribution with a mean of 25 minutes and a standard deviation of 10 minutes. Based on what you learned in this video, you need to explain how you expect the queuing performance measures to change. Now remember, the measures we're interested in a typical queuing problem are the utilization and waiting time in the queue, waiting time in the station, average number in queue, average number in station. So for each station A through D, you need to explain whether these measures increase, decrease, or remain the same based on what you learned. Also, you need to explain how you would expect the average time an entity spends in the whole system, as well as the number in system to change. In the second case, we have the original queuing network without the machine failure considered in case 1. But this time, we are going to change all service time distributions from exponential to a symmetric triangular distribution with the same mean processing time. Again, you will need to develop expectations about how the performance measures for individual stations, as well as the average time and number in system, would change. In other words, which one goes up, which one goes down, and which one stays the same. After you finish this activity, to see if your answers are correct or not, I highly suggest that you try building a simulation model of this queuing network, and then try to implement the above two cases, or the two cases that we just discussed, to observe how the steady state performance measures actually change, and see if your expectations were correct. This concludes our video session on advanced queuing models. If you want to learn more about the queuing models discussed in this video, you can refer to the textbook by Curry and Feldman that is provided here. Thank you for watching this video.